Now we can look at the autoionization of water, which just means that water can self-ionize. So we said water is amphoteric, right? It can act as an acid or a base. And so that's what amphoteric, we said it was amphiprotic before, which said it could gain or lose a proton. So amphoteric just means it can act as an acid or a base. And so when you have water, so in pure water, some of the molecules are going to act as an acid, some of the molecules are going to act as a base. And so we have this reaction happening. You have water, one of these water molecules is going to act as an acid. One of these waters will act as an acid, one will act as a base. So if this is an acid, it's going to donate the proton over there. So one will lose one and become the hydroxide, and one will be the hydronium. This doesn't happen to any great extent. If you look at the equilibrium constant for this, 1 times 10 to the negative 14, this is at 25 degrees Celsius. If you change the temperature, this number will change a little bit. But 1 times 10 to the negative 14, that's not really a lot. This isn't really happening. Most of the water just looks like water. But we can use this equation. This always has to be true as long as you're at 25 degrees Celsius. The hydronium times hydroxide has to equal that number. So that means if you know the hydronium concentration, you can figure out the hydroxide, because this is a constant. This is the equilibrium constant. Just if you want to see this kind of drawn out as like Lewis structures, here we have a water and a water. And then here we have water, right? 2 water molecules. The one that acts as an acid is going to donate the proton over here, and so you end up with your hydroxide ion and your hydronium ion. And so if you know one of these concentrations, you can figure out what the other one is. And so that's what we're going to do in this next section. So here in this problem in 1614, I'll just put that equation down there again because we'll use that a bunch. They're giving you the hydronium concentration. One of the books that we're using says hydronium, the other one says H+. For our purposes, it's the same thing. If you see H+ or hydronium, it's the hydronium concentration. That's what we're talking about. So in this problem, they say H+ is 2 times 10 to the negative 6. So that means you know what this is, and they're asking you to find the hydroxide ion concentration. So you can just plug that number into that equation. So if I just took this and I plugged it into this equation here, I have 2 times 10 to the negative 6 times hydroxide is 1 times 10 to the negative 14. So then you divide by 2 times 10 to the negative 6 on both sides, divided by 2 times 10 to the negative 6. And then when you work that out, and take a minute, plug it in your calculator, make sure that if you're not using your if you're using your times 10 button instead of your EE button, that this whole thing is in parentheses. Otherwise, you'll get the right number with the wrong exponent. That happens a lot. So when you work all this out, you get 5 times 10 to the negative 9. Whoa. 5 times 10 to the negative 9. Negative 9. And that's a molar concentration. Now, when hydronium and hydroxide are the same concentration, then you can just plug in hydroxide, or you're trying to solve for the hydroxide, so you can plug in hydronium over there for the hydroxide concentration, right? So you have basically hydroxide, because you're trying to solve for hydroxide, times hydroxide. So if they're the same, all I did was I put hydroxide in here for the hydronium. So I end up with hydroxide squared is 1 times 10 to the negative 14. So I just have to take the square root of that, and I get the hydroxide concentration is just 1 times 10 to the negative 7 molar for that one. And I should have given you way more space here. And then the last thing you want to do is here, I'm just going to erase these so it's a little bit clearer what I'm doing. Wherever I have hydronium there, since I'm looking for hydroxide, I'm going to take this and plug that in for hydronium. Remember, H+ is the same as H3O+. So when I plug that in, I get 100 times hydroxide. That's what the hydronium is, right? So that's hydronium times hydroxide is the 1 times 10 to the negative 14. So I can divide this by 100. Right, that cancels that, and then I take the square root of both sides because I just want to solve for 1 hydroxide, and you get hydroxide ion concentration of 1 times 10 to the negative 8. 1 times 10 to the negative 8 molar. Actually, this one should just be not with a 1.0, which is just 1. I only have 1. Do I have 1 sig fig? Oh no, I do have 2. We're good. There's 2 sig figs there. This one only has 1 sig fig. All right. And there we go.